The title of the next presentation is 5 AI/ML related things that you didn't know that you could do on Teradata. This was the presentation title that we discussed and agreed with Chris, I want to say 2 months ago.
2 months ago.
And then we've all told you about the 5 things he was going to tell you about. So you do now know that those things can run on Teradata. And so this presentation has adapted, like all the best presentations do. And Chris is now joined by 2 special friends. Martin Hillerbrand, or Young Martin, as he's known, and Alexander Smirnov, or Sasha Smirnov, as he's known. And these guys are the good, the bad, and the ugly. There's a short competition. You can tell me which one is which at the end of the session. But these guys are going to double-click on those 5 use cases. And so without further ado, guys, over to you.
Cheers, thanks. So, yeah, because I was so organized and did everything as I was supposed to, everyone got my slides first and then stole all my use cases for their presentations on the stage. So I renamed this now to 5 AI/ML use cases that everyone's just told you can do on Teradata. So I thought to mix it up, I'd actually bring in the people that have done the actual work, because, you know, there's no smoke and mirrors here. These were real projects and we did the actual work. So, you know, we're a fairly intimate crowd, and Kevin hasn't done enough this couple of days. So I think you just ask questions all the way through if you want to. Just, you know, put your hand up, grab the mic, or we can do questions after each, whichever. But if you just want to find out, because all of us, me, Martin, and Sasha, tend to speak quite fast. So if you want to like something repeated, or what did you really say there, then please do just let us know. So the first case we're talking about is the anomaly detection on outstanding debt amounts. So this is a good case, and it's a class of cases, okay, that we would call a imbalanced class. Okay, so it's in the same kind of line as like fraud and a lot of anomalous stuff where you've got like, again, I have to put that down so I don't touch it. So you've got like, you might have like hundreds of millions of cases that aren't anomalies, and a small amount that is anomalous. Now the problem with imbalanced classes is you need to see much more of the data than you normally would. So you would normally be able to work with samples, surprisingly small samples in some cases. This is doing this on its own. I'm not touching it. If it does it again, we'll just leave it. So surprisingly small samples, and that's how you can get away with using systems where you can extract data, put it somewhere else, and you know you don't worry about the data movement. But in these type of cases, you often want to see all the data in one case, because if you take out a small sample, the chances are you're not going to get any of the anomalous cases in it. So if you're trying to train a model, that's pointless because you've missed it all. So this is one of the things that the in-database functionality of Teradata like shines at, because you can do all that processing in the database without moving any data around. So if we look at the 2 different ways, the different parts of this, the in-database processing was done on the feature engineering, which Martin will talk to you about. But also then when it comes to the model training, we've talked quite a bit about bring your own model, where you can train models outside the database and then bring them back in. Well, you can actually train Python models in the database as well. You probably haven't heard that bit. So this is a really nice example of mixing and matching like our proprietary work and open source in a workflow that no data moved anywhere. It all just stayed in the database. So first, I'll talk to you about the feature engineering and the kind of work that was done on that, Martin. Yeah?
Yeah, I definitely can talk about that. So why do you do feature engineering in general? So this obviously was like a time series problem. So you had transactions, sum of transactions every month, and at some point it would be an outlier. It would be an anomaly. And for regulatory reason, this customer, this bank, needed to kind of dig deeper if they thought something was an outlier. It could be bad data, it could be actually some wrong calculations. And they had a system in place, but it was based on a single rule. It basically said if it's 15% above or below the average of the previous month's data, it's an outlier. And guess what? They had 15,000 alerts a month. Nobody ever could like work or dig in 15,000 flagged anomalies. And a data scientist typically does feature engineering to get different perspectives on the data. So the 15% threshold flag might be one feature. But with our in-database capabilities and just some creative query writing to get features, we had lots more angles on the data. So first step would be then maybe have a handwritten rule on top of these features. So if it's above or below 15%, and if there was no trend in the data and so on, you would have an outlier flag. But the next step is, instead of having a manual rule, you will want to have a machine learning model that automatically would detect an outlier. And this is why we deployed one class support vector machine there.
So I was just going to say, actually, I've got to say, that is actually a kind of characteristic of these imbalanced class problems, that you tend to get lots of false positives. So you'd have a load of alarms for stuff that wasn't actually a problem, and it's because it's difficult to train the model with that kind of imbalanced class, isn't it? Yeah. So the one class SVM was done with, that's Python code,
yes.
is it?
Yes,
right,
it
okay,
is.
so that's where...
Scikit-learn.
Yeah.
Exactly. And then the thing is with your classic bring your model story. Who in the audience knows our bring your model capability in Teradata?
Everyone knows it.
Yeah, everybody knows it. So basically you prep all the data in database, you pull them out, you train a model, you push back the model in database, and then you can do the inference in database where the data already resides. So it's super easy, super smooth deployment. However, with this customer, we didn't have the chance to actually pull the data out of Teradata. So we used a little trick. We used script table operator, which allows us to spawn Python processes on all the parallel workers, on all the amps. But we only did it on one amp. For a very small model, for this one class support vector machine, we put it into the exchange from what the bring your model would expect, and thus just put it back from one amp to all the other amps. So we had bring your own model through script table operator in this context.
And we'll move on in a bit, but there was a particular reason for that, because of the way the DBAs work with SQL, wasn't there? They wouldn't let us execute Python because they didn't trust
couldn't
us,
deploy
basically,
Python. They couldn't deploy Python.
Right,
yeah.
right.
But if you just hand over the Python code, they could install the Python file on Vantage, and the deployment would be the calling of the script table operator.
Which is SQL.
Yes.
And that's the key thing. So although we'd done the work in Python and it was running in a Python instance in the database, the control and the calling and the execution was all SQL based. It's complicated, right? So yeah, but it's just a good example of how flexible the system is to cope with all these different implementation patterns, and how in our proprietary algorithms that we rewrite in parallel, we're never going to keep up with open source. How could we? But that doesn't matter to us because we're open to any of the open source algorithms. Good. Okay. So the next case, I actually haven't got the expert who did this here, so I'll talk through it in a very bad way. But this was the case of the medical thing. This was talked about quite a lot, and basically. We were processing medical images. This was actually from mammograms, directly in the database. Okay, so the files were coming in off the machine. We were picking them up through an object store, and then in the Cloud Lake Cloud Lake offering, let's get that right, Vantage Cloud Lake offering, we have a thing called the Open Analytic Framework, and it's a bit like Martin was just talking about, the STO, script table operator, but it sits outside the database in containers. So it's much more, let's say, DBA friendly. You're not saying to the DBA, we're going to run Python code in your database, and he's like, no, you're not. We're saying we're going to run Python code in this container next to the database. But what it allows us to do, basically, is do this was all about actually image processing, because the kind of the image extraction or the feature extraction from these mammograms is kind of a solved problem. There's nothing particularly spectacular about that now. But the ability to be able to take many of these files and process them in parallel, because it's not just a case of taking the image. These machines create a file format called DICOM, which nothing else can understand. So we actually use another library to interpret it, and then you were doing all kinds of work in enhancing the images and the contrast. But we could do that in a massively parallel fashion now, because each of the images are completely independent, and you can process them in completely different ways. So it was a really good way of doing it. It was a really good system. But of course, that's still not really a good enough reason to put this onto a Teradata system. And what really the company involved wanted to use it for was the fact that it was actually joining that back to the medical records that was the problem, because you couldn't have that data moving across systems. It was highly secure, highly private. So to be able to do this processing, to be able to take the mammogram images and then to process them and get the results and then join them back to medical records all in the same place was the reason why they decided to do this way with us. So that's another way of doing kind of open source work, but inside the Vantage platform. So, and just right, you can ask questions at any time, but not about this one, because I didn't do the work, okay? So don't, yeah. The other ones, please ask whatever questions you want. But, okay, so this one, Steve McMillan kind of referenced this, and it was doing the video. So that one was like medical images. This is actually video processing directly in the database. And this was Vantage Enterprise, so this isn't using any of the Cloud Lake capability. It's actually in the Enterprise edition. So the idea here again is to take the video feed from the car, work out certain features about that video, which Sasha will talk about, and then again, you know, that's not that earth-shattering as a task. You know, you've been able to do that computer vision for quite a while. But then joining that to terabytes of sensor data from all the telemetry from the car and being able to process that all in the same place and align the timestamps and all this kind of thing, that was the tough bit of the job. It's almost like it keeps coming back to the tough bit of the job, the data integration, and it kind of is in some ways. But yeah, what was great, we could do this all in one place and using our Enterprise edition, which means it could be effectively an on-premise solution. So it could be trackside, which, you know, so we were kind of taking that, all that innovation that's going on in the cloud, but pushing it down into a system you could run on-premise. So I don't know if you give some more details on that, Sasha. Particularly is interesting is how you did the computer vision task.
Yes, of course. Yeah, that's...
the mic.
That's... Oh, I have my mic.
Oh, you got a mic, oh.
Yeah, I'm not like him, I like small mics. What I was saying, that's the little architectural diagram, or the workflow diagram, how we actually were solving this problem of the video processing on Teradata. Actually, in the heart of the whole stuff, it's two sides. It's fine-tuning and training of the model, and that's an inference side. And on both sides, we are using the OpenCV framework. That was the most innovative part of the whole stuff. So I developed the function for Teradata, actually not one function, but a bunch of the functions, which I called Teradata CV framework, kind of cool name, isn't it? Which is actually exposes a number of the functions existing in the classical OpenCV library, which is like a standard for years, if not say decades, in terms of the video processing. And we can process the video using these capabilities of OpenCV right on a Teradata nodes. Saying process video, I need to dig a little deeper on what I mean saying process the video. The whole idea of this Teradata CV framework is 4-step processing. First step is reading the native format, reading the data from where it stores. It could be two options. It could be a native object store or anything which can expose the S3-like API, or it could be videos could be stored on in the blob records in Teradata tables. Second step is parsing this video. On the input, we have a video file like MPEG or whatever other format you have. And on the output, we have a bunch of the records, binary records, where one record represents one frame. Then next step is pre-processing. So basically all the operations you're typically doing on the images, like resizing, rotating, cropping, all the standard stuff. And the final fourth step is applying some logic to these frames, like you could apply model, you can do OCR, optical character recognition, or you can basically save them as the images, whatever you want. And using this four-step framework, first we prepare the data for model training or the fine-tuning, and that's another interesting thing. Here we use very simple model because the image recognition models, they are right now reach the stage of maturity where they are like really, really lightweight. They can work on the, I'd not say it like on your cell phones because our cell phones is pretty powerful computers. I want to say they work on the tiny cameras on a very cheap edge computing storage. So I mean, why I'm saying this because the models, this image recognition models, they're super lightweight on the execution and lightweight on training. So we took one of these super light models, we fine-tuned it to detect objects we want to detect from the video stream. Everything was done using CPUs, even the fine-tuning was done using CPUs. And we deployed this model in the Onyx format to Teradata. And for the inference on the right-hand side, we had a very simple situation when we have the video stored in the native object store. And then we do the parsing of this video and apply our model to the frames. On the output, we have a table, classical database table where we have file name, timestamp of the frame, number of the frame, and the result of the recognitions there. And then this table was able to be joined with other data sets like telemetry and other stuff.
It's kind of process I like, I've been calling AI for feature extraction. So it's not, you know, it is AI/ML, it is predictive analytics, but what we're actually trying to do is get something out of a complex data type, like an image, and then turn that into a feature that we can use somewhere else. So that's the idea of AI for feature extraction. And I think, Sasha, this was probably one of the first times we'd used a pre-trained model from somewhere else.
Oh,
and
yes,
fine-tuned it, which is becoming an increasingly popular pattern. So rather than training a model yourself, you take one like this computer vision model, you fine-tune it on your domain, your data set, and then you use it somewhere else. I think it's probably one of the first times we've done it.
Yeah, Chris, you're totally right. I totally agree with you.
And this is why one of the, sorry, I'm laughing now. Sasha's trademark is if anyone says anything, he starts the answer with, I don't agree with you. But so now you saying that, you're taking a mick now.
Chris,
so, yeah,
you're
so,
absolutely right.
So, you know, the fact we can do, so it's often like, you know, why are we doing this now? And we haven't been able to do this before, and it's because a lot has changed. A lot has changed. Partly it's Teradata's openness to be able to do this, which, you know, in the last few years has really changed. It's partly the fact that these fine-tuned, these pre-trained models exist, which they never did. And it's also, as you said, all that innovation around computer vision, which means it can run on your phone, means we have no problem running this in the database without any, you know, it doesn't go in near a GPU, does it? So, yeah. Okay, that's good. So the next case, now this is interesting. This is the LSTM case that Martin talked about in great depth today, so you set us a high. And what's quite funny is this was actually about oil pumps, and I'm assuming that marketing didn't know what oil pump looked like, so they've given me a picture of a satellite tower.
They are easily confused.
Yeah, I mean, yeah, cell tower, oil pump. But yeah, it's I shouldn't say anything bad about marketing, they're listening. So anyway, and what was quite funny is in the bar well, there was a lot of things said in the bar last night, and a lot of it I would never repeat, but one of the guys in the bar last night said, why is anyone still using LSTMs? Come on. This was like a year and a half ago, 18 months ago?
Yeah.
Why is anyone still using LSTMs? And I said to him, well, what algorithm are you using for your churn model? And he said, logistic regression, didn't he? And I said, so you can shut up, right? Because if if it works, it works. Just use what works. There's nothing wrong with logistic regression. Anyway, so yeah, long short-term memory model. It's an RNN. I guess that's why you're saying we're still using it, because RNN is a little bit out of favor.
LSTM are big. They have a big comeback right now.
But yeah, it's a difference between like, you know, what you read about it and people actually doing the actual work, isn't it, I suppose? Anyway, so yeah, the idea was this was already a project that had been tried, and they'd done all the model, the feature engineering was Spark again, is it?
Yeah, mixture of Spark and Python.
Yeah, mixture of Spark and Python. And they tried building this as like a single model, okay? So, and the problem was the performance was poor right across the thing. So Martin came in.
Yeah, and it was not like a single model. They still like had multiple models,
they had multiple
but
models.
they trained them in sequence. So it good old for loop.
It wasn't parallel. Okay.
Yeah.
Can't beat a for loop. And again, not a GPU inside. Because when you came back and said, I've just trained all these models in the database, I was like, how the hell have you done that? But yeah, you can talk to people about the secret sauce behind it, Martin, I guess, yeah.
Yeah, I mean, one thing that is important, you already said it, is this was already project done in terms of the code was written in PySpark and in Python and LSTM and everything. So our task, or basically my job, was not to come up with the logic and the use case, but to show that we can do it more efficiently. Because they really struggled with the deployment part. So for the inference part, they had a very small use case deployment for 24 pumps times, I think it was 14 target variables. So this was the dimensionality of how many models they have trained and need to put in production. And they wanted to make a prediction for different target variables every hour for every pump. And they barely finished in time. So it was 58 minutes something that they've reached with an already tuned solution. But they don't just have 20 pumps, they have many more pumps. So they couldn't scale out, basically. Yeah, so long story short, I got the code. It was like 10,000 lines of code. I picked out some example where I easily could showcase how much easier it is with us. One part is data ingestion. That is what was done by a great colleague. JSON shredding, super fast. Then I picked out some data engineering functions where they used a mixture of PySpark and native Python on a single thread. I just translated everything into Teradata ML and SQL. I wish I had PySpark to Teradata ML at that point, but I did it manually with a little help of ChatGPT. And we could already, for the feature engineering and data preprocessing, shrunk down the processing time from 300 seconds to about 30 seconds on the smallest POC system available. And as you can see, massive parallel system, you can scale out very easily. And now comes the sexy part, the LSTM. And as I said earlier, I'm kind of like a glorified for loop spotter. So whenever you have a code that takes too long and you find a for loop in it, that might be the cause. Because if you have a single-threaded Python environment where you train model after model, well, it's just how long does it take to train one model times the number of models you've got. And script table operator is kind of the perfect solution for it. So I also ask you if you have any solutions in place where you struggle with runtime, but where you have a for loop, that might be just one case for us. And yeah, it was many small models trained on small partition of the entire data set, like 10,000 rows for every model. But again, if you run 500 models in SQL, it takes 500 times 5 minutes. With parallelization, it gets divided by the number of amps, number of parallel workers in our system. Plus, you have no data movement. And that was kind of the secret sauce. I didn't really change the code. I just put it in the script table operator framework. And that's basically it.
So the idea is using that parallelism on Python code. It's important that you segment the data, otherwise you'll get the wrong answer. Okay, you can't do averages of averages. You need the sum of the count and come back to a single point. But in this case, each of those segmented models could be built on its own partition of data with no reference to any of the others. So if you've got like a 10-node system, you could have 480 amps, that's 480 units of parallelism. You could almost do this in just a single pass. And then if you've then got, 4,800 models, you'd only need 10 passes to do the entire lot. So that, we call it hypersegmentation. It works with things like demand forecasting. If you've got 10,000
arbitrary
stores
Python code you can execute.
Yeah, that's right. Yeah, where you can partition the data and you can train a model on that partition, really, really, really efficient. So there you go. And there's nothing wrong with LSTM models. Let's just clear that up. So the last case we're talking about, been talked about a few times. I know that it's mentioned on the stage. I know Gary did a really good session on this, but I don't know how much detail you went into, Gary, but I'm sure we can beat you on that. A little bit. Now, this is actually quite a complex setup, isn't it, Sasha? So we'll try and break it down into the individual parts. So the first thing is, it's a RAG workflow. I take it everyone understands a RAG workflow? Yeah, so we're using the vector embeddings to query. We're querying the vector embeddings that are being created from text, and that is helping us. It's helping us to get new information into the system that you can query, and it's also helping us to not have things like the hallucinations and stuff like that. So the way I like to describe this is, if you've got a task you're trying to do, which could be, let's say, topic detection in a text, okay? You can send that through an API to Claude, Gemini, GPT, and you can get the answer back, okay? And it works really well. You've got to pay the other end, by the way, but it does work. But do you really need a tool that could take that email, rewrite it as a Shakespeare play, and give it back to you, right? Because ChatGPT could do that. Or do you need something that can do topic detection on that email, just that single task? So I think I don't want to use the word genius with you, Sasha, because you're already bad enough anyway. But the genius of this was taking that task, splitting it into smaller task-specific things, like embeddings, topic detection, summarization, semantic search, and then using the pre-trained models to do each task as it's supposed to be. So I don't know if you want to talk people through the kind of flow and your thinking at the time.
If you don't mind, first of all, thank you very much, Chris. That was very correct and right explanation of what was done. I totally agree with everything I was saying. Let me just add a couple of details here. How does this workflow of processing data in a such manner works? So first of all, we have a model. And the model we used in this project, that was a model from a Hugging Face repository. Obviously, as Chris already said, these open source models became more and more popular. And I can tell you what, I was talking to one customer who used to spend like half a year on a project of fine-tuning the model for their own needs, the model taken from a Hugging Face repository. Then they've spent half a year, a lot of resources to fine-tune this model. And the customer told me that, Sasha, if only I knew like what the results will be, I will never go for this. I will use just a plain model from a Hugging Face repository and save this time and effort. So yeah, it became more and more popular. So we're taking one of the models from a Hugging Face repository, and we deploy this model to Teradata database. I want to be very clear here. That's exactly the case because we hear a lot about running the language models on the CPUs. That's exactly the case where we run the language models on the CPUs. I don't want to create the wrong impression that you can take like any crazy huge model like whatever size and run it on the CPU. No. We used the models on the smaller size, something like 100 million parameters, 150 million parameters, something like this. These kinds of the models, they give a result which is good enough. There was no questions about like how good the result we get, but also they're very lightweight on the execution. They're very light on in terms of the consumption of the computational resources. So we take this model and we deploy this model into the database. But before get the data to the model, the data needs to pass through the certain stages. It needs to be properly chunked into the smaller pieces, and it needs to be tokenized. Another thing we did, we create a function for Teradata which supports the tokenization process for all the models, or for the standard for the tokenizers existing on a Hugging Face, let's say, community.
And actually, just on that process, tokenization is a key bit in these language models that people, you you don't hear about it as part of the process, but it's actually a big part of the process.
Yeah.
And every model has typically got its own tokenization process, hasn't it? You have to keep changing it every time you use a different model.
Yeah, it pretty much it is, and that's actually very funny because when we say like language models or large language models, we typically think that these models works with the text. No, in reality, as any normal model, these models work with the numbers on input, and the tokenization process is the process of the conversion of the input text into the numbers, basically, most typically by vocabulary. And then these numbers already feed it to the model. So, as I said, our job was to pre-process the data, use the model to convert pre-processed data into the embeddings and store these embeddings into it's a very posh name for this embedding store, but in reality that's a table with the vectors. So we're saving the data, these vectors there, and then after this we can perform so-called semantic search on the top of this. So basically the search using the cosine similarity distance measurements, and we can, for instance, in this specific bank, how it was done. They created the table with the topics. So basically, descriptions of the topics. Like, is it the email about broken ATMs? Is it an email about, I don't know, aggressive behavior of the teller, sales pressure, whatever. And on a daily manner, the new batch of incoming communications were calculated the distance or the similarity to each of these topics, and on the output you have a table where you have the email, basically email ID, and the likelihood to each of these topics. And then on the top of this you can do your business cases. You can dispatch the emails or the complaints to a specific department. You can build a dashboard where you will see the systematic issues, like, I don't know, in this specific region there is a problem with the ATMs, there are a lot of complaints about, I don't know, aggressive teller behavior or something like this. And the most interesting thing is they said that they can even increase the knowledge about their own customers through this. So basically, if you have your classical customer 360 data mart on the top of which you're building all your classical models like churn, marketing segmentation, whatever, you can add new features into this customer 360. Features like days since last complaint about the ATMs. Were there any complaints about sales pressure in the last 30 days? And this new knowledge about the customer, which you got through the communication, through the properly processed inbound communication from the customer, can also increase your understanding of the customer and your classical models.
And of course, the whole process now, completely in database and separated in smaller tasks. So, where we're all thinking about this EU AI Act and how we're going to go with this, what happens if you get the wrong answer. In this kind of workflow, you can check each stage of the process. You can say, was this where it went wrong? Was that where it went wrong? Was it the search? Was it this? And using the vector capability, if your answer's wrong, you can say, why was that matching? You can see why the matching was wrong. So I quite like it. I don't know if we're going to call it this meter, but you like the term private Gen AI, didn't you? It's kind of like, it's private to you. Nothing here is going out of your system or to any cloud provider or to any third party, any third party vendor. So yeah, that's good. I think that's us. Yeah, that's good.
And I think it's time for the questions.
Thank you to my glamorous assistants.
So before I throw it open to the floor and I give you guys chances to ask questions, I guess I'll pull out a couple of things that I think are really interesting. When we were talking about the anomaly detection and we were talking about bring your own model and somebody pointed out that we've talked about bring your own model a lot, but that was a particularly innovative use of bring your own model. There's a number of things that are really nice about bring your own model, but one of the things that we haven't talked about so much the last couple of days is the kind of separation of duties thing as well, right? It creates a very natural break point in the process. So you can have the data scientists do what they're brilliant at doing, which is innovating and creating models, and you have this natural point where that then gets handed over to an IT ops team, because the team that is brilliant at innovating and building the models is not necessarily the same team that's great at standing up and running a production service, not necessarily the same group of people that wants to carry a pager and get called at 2 o'clock in the morning when stuff breaks. I think that's actually a really interesting thing about bring your own model.
The other thing, of course, is you get a total separation between your development server and your production server. There's no dependencies between the two at all. It doesn't matter whether you use Python, whatever version, whichever library. The ONNX format actually creates a complete separation between the two platforms.
So another 2 reasons to think about bring your own model. When we were talking about video classification, and Chris used this expression that we use quite a lot, which is this idea of AI for feature extraction. In the end, the same thing that Gary was talking about this morning, right? You know, the objective of the exercise is not to use AI for AI's sake. It's to try and understand, is that call a complaint? Is the issue a card? Is the issue a payment? And we see that AI for feature extraction process over and over and over again. And when we were talking about the medical imaging, again, you know, there are a number of reasons to think about Teradata for these workloads. Scale, speed, but actually, precisely because very often what we're doing is AI for feature extraction, the next step in the chain is to integrate the insight that we've just created with all of the other data that we have about the car or the customer or wherever else. And obviously, not only is that data very often in Teradata, but Teradata is a very high-performance platform for joining different data sets together. So I think that's worth calling out. The other thing that I think is really interesting about the kind of image and the video classification, just kind of philosophically, I remember Chris and I having a drunken conversation years ago. There have been quite a few of those over the years. And you know, when we talk about classical feature engineering, very often we're talking about things like taking ratios, binning variables, that kind of stuff. And we were saying, well, in an AI future when we're mostly dealing with multi-structured data, does all that go away? And actually, Sasha kind of touched on this briefly when he was talking, but I think my experience anyway is, no, not really. So the image data is fascinating. When you look at those data pipelines for images, there's still a lot of data processing. You are resizing images, you're cropping images, you're sometimes rotating images to increase the size of the data set, you're normalizing the red, green, blue channels. It's not like the feature engineering we grew up with. If, like me, you kind of grew up with GLM, but there is still a lot of data preparation work in those tasks. And then the LSTM stuff, the preventative maintenance, glorified for loop spotter. I'm going to get t-shirts made. That's fantastic.
Sorry, what do you?
Glorified for loop spotter. Is that what you said? I'm going to get t-shirts.
Oh, yeah.
We're going to get t-shirts. We're going to get team t-shirts. I thought that was beautiful. And then lastly on that voice of the customer piece again, this point about pre-trained models is kind of really interesting, right? I think, you know, we are a long way away from a point where we're going to use pre-trained models for all the tasks that we care about for AI and machine learning. But this repository of pre-trained models, which are good enough for lots of functions. I thought that the anecdote you told about, you know, your colleague who was like, if I'd only known, I spent 6 months fine-tuning for 1% lift. Why did I bother? I should have just built the workflow.
I can add here that I prefer to think about this Hugging Face repository and open and this, let's say, publicly available models. It's the same old story. It's an open source software. That's it. But the open source models and the Hugging Face repository is like a new GitHub. That's it.
So, very cool stuff. Anyway, those were my observations. Have any of you guys got questions? Because there you go. Mark's got a question.
The last use case, voice of the customer, that essentially is a batch process, right?
Yes.
Yeah. So, can you go back to the last slide, please? This one here. It's that process there. How real time can we make that? Because actually, if you're not scoring this or not processing against a whole batch of stuff coming from all customer inputs.
All it really needs is to be able to tokenize and vectorize, if that's a new verb we're going to use. Vectorize, come on.
Because if you go on, again, the previous slide,
Yeah.
please, there was a reference button to a augmented intelligence application. And I'm wondering what that is. Because what I'm trying to get to is, if you have voice of the customer coming through a channel, let's say mobile banking channel, for example, and you can react that really quickly based on that sentiment, and you integrate with messaging, like VCX and messaging, for example, you've got that feedback loop straight. So that's real time. That'd be amazing.
No, it would be good. I mean, the thing is, this was specifically for email, so you're not going to be replying to emails in real time, really, near real time. Any of those mobile channels, I would imagine the message would be much shorter.
Yeah.
Yeah. I don't know if you thought about that, Gary, in the work, but this was very much for kind of email processing, wasn't it? So it was a batch process, like you say. But it all depends on how quickly you can tokenize and vectorize that model so you can do the semantic search. You've got to get that bit done.
And I think, I mean, help me out here, Gary and Chris. I mean, I think you're absolutely right to regard this as a kind of batch process, right? And one of the reasons it was a batch process for this particular institution is there were 2 years of email history or something that needed to be processed. There's a big historical archive. But it's the kind of user query where you're creating an embedding from the user query and then comparing that, essentially doing a similarity search with all the other embeddings. There's no reason that that needs to be a batch operation.
No.
And you know, one of the things that, again, people don't necessarily understand about Teradata that we'd like them to is that we've got these really powerful kind of vector distance calculations, and that set of vector distance calculations is probably about to get richer as well, right? With some approximate nearest neighbor searches as well as kind of deterministic searches, and that should put some even more gas in the tank in terms of the ability to support those lower latency workloads.
I'd like to validate that kind of real-time potential with the customer in mind first, but I'd like to take that further if possible.
Yeah, that'd be good.
I just have one comment, which is, this was for a risk application, so it was a necessity. Doing some type of evaluation. Although this, one that I was speech analytics, and the real concern here is access to actual digital call recordings, which is kind of a pleasure capture, and getting access to the recording call recordings is actually a constraint. The limits of the ability to use real time.
But if you've got access to that input, that speech, you know, the voice conversation, for example, there's all sorts of inference from inflections of tone of voice, not just sentiment. It's all sorts of things there.
I can say that there are vendors out there that
Yeah.
very expensive, and they actually work to control access to call recordings.
Yeah. Okay, thank you.
And Mark, to your question, I would like to add that this first part, which is the tokenization and converting to the embeddings, that's a bring-your-own model. And you know better than me that bring-your-own model can run in real time. Just a half a year of a sleepless night and you got the millisecond processing. You know that.
250 milliseconds.
I said milliseconds.
250 milliseconds. Any other questions out there? Because you're all very nice to the guys during their presentation, so this is your opportunity to be nasty to them if you want now. I guess you must have done such an outstanding job that there are just no questions left. Let us show our appreciation, please, to Dr. Rock, young Martin and Sasha.